Good evening, everyone. Today is the eighth discussion hour of this course, and before we start today's agenda, I'd like to just have a quick summary of what we have discussed so far about manipulators and how does it basically form a foundation for the upcoming discussion on motion planning and control. So I'll just describe the bigger picture once again so that we know where do we stand at this point in our discussion of manipulators, their dynamics, and the controls. Is the screen visible? Can you confirm in the chat? Okay, sure, thanks. So we started uh, with an objective of basically if we have a system that has multiple bodies attached and attached via joints, those so we the initial description that we gave that we have multiple bodies which are rigid in our entire discussion of this course, the links that or the bodies, each individual bodies as we call them, links. So these links are basically attached to each other and via joints. So we have rigid links, and secondly we have joints. And in most of our discussions we have seen the revolute joint and the prismatic joint, and occasionally we have seen the spherical joint. There could be other types of joint as well, and we had earlier in the course we have seen a table in which different joints have been listed down. After that we discussed the concept of degrees of freedom, which is the fundamental concept uh, which describes that how many independent variables are required in order to fully describe the configuration of this multi-body system, right? Because if we want to analyze the movement of the system from one configuration to the other configuration, then we must first know how to describe the configuration of the system. So, and for the dimensionality of that space in which the configuration is described is the degree of freedom. Now, after that, we discussed what are the different spaces. So, representation of configuration, and we discussed about the joint space and the Cartesian space, which we will revisit once again in this discussion as well. So joint space uh, is the description using the joint variables. Let's say if the joint is a revolute joint, then the joint variable is the uh, angular position of that joint. In case of a prismatic joint, sorry, that's the uh, translational variable, that what's the linear position of the joint, and similarly in case of other joints as well. While in the Cartesian space, we describe the position of the end effector or any point of interest on the multi-body system that we have in the Euclidean space, that is the three-dimensional space in which we basically work in. And if we are concerned with the entire position and orientation, that is the pose of the end effector or the robot, then the description is given in the in the combined space of position and orientation. So that is given in the SE3 space, special Euclidean group. which is the homogeneous transformations that we discussed, in which here comes the rotation matrix 3 cross 3, and here was the translational part 3 cross 1, and here zeros, and 1 is the scaling factor. So this representation combines the entire information in a very condensed form, and can be used to describe the relationships between one frame to another frame, right? So once we describe, once we are able to describe the configurations, and in the process of describing the configurations, we discussed about the conventions of frames. So one of the more popular ones is the DH convention, but uh, that is not something, which is a rule that cannot be violated. Basically, you can assign different frames as well, unless they do not violate the orthogonality of the axis. Uh, but DH parameter has been used for a long time now, and has become a standard in textbooks, and also various, let's say, code bases that you refer to. So that's a good thing to refer to. Once we describe the configuration and the frames, then we start our discussion of the mathematical model. So then this discussion was split into two parts. One was kinematics, and the other was dynamics. So let me just continue right from here. I'll go back here. Okay, so we had two verticals in the mathematical model, the kinematics and the dynamics. And kinematics is the study analysis of the motion without being concerned about the cause, while dynamics is the study of the agency of motion, that is, with its cause. So here we study about uh, the positions, the velocities, and here we study about the forces and the moments and accelerations. So in kinematics, we discussed about the position and velocity of different links of the multi-body system. Basically, we could write the position of any link in the Cartesian space given the configuration in the joint space by using the forward kinematics. And if we have the position in the Cartesian space, then we can very well find out the configuration in the joint space using inverse kinematics. So we discussed the concepts of forward kinematics, inverse kinematics, and a special matrix, which relates the transformation from joint space to the Cartesian space, is the Jacobian. So by now you would have seen that this matrix Jacobian is, at the very center of analysis of multi-body systems. So basically, the relation that change in the position, in the Cartesian position of a point on the multi-body system, is the Jacobian of that point multiplied by the change in the angles. So basically Jacobian relates that if I change the angles by a small amount, then what is the change in the position that I would expect to happen for that point. And more often than not, that point is the end effector, which in which we are interested in. But one should remember that Jacobians can be written for any point on the multi-body system. So you can write, let's say, Jacobian for the center of mass of the second link in a 3R manipulator, right? So it's not limited to just the end effector. Uh, for any point, if you want to analyze the relation between the change in the joint angles to the change in the Cartesian position, then we must find out the Jacobian. And Jacobian is a frame dependent quantity. So we saw that the Jacobian of the end effector has a different representation in the frame of the end effector and has a different representation in the frame of the in the base frame, basically, right? So and we have to be careful that let's say if I multiply del q or change in joint angles with Jacobian, which is expressed in the end effector frame, then delta x that I will get will also be in the end effector frame. And if I multiply the Jacobian that is expressed in the world frame or the base frame, then the delta x would be in the world frame or the base frame. So while doing transformations from joint space to the Cartesian space or the operational space, we have to be careful that what is the frame in which our Jacobian is being expressed. It frame. And like any other quantity, Jacobians can also be transformed using rotation matrices. So if you have rotation matrix that describes the relative orientation of the end effector frame with respect to the base frame, then you can very well transform the Jacobian itself and you need not calculate it separately. So by the end of discussion on kinematics, we were able to describe the relation between joint velocities and the uh, end effector velocities, and we were able to do inverse kinematics and forward kinematics, and we also saw about the concepts or discuss the concepts of reachability, manipulability, the workspace, singular configurations, which are all related concepts which help us, give us a more sort of practical picture of what are the key things that we should know when we try to work with manipulators. Let's say we would just now in today's discussion we would see that how to plan trajectories, and while planning trajectories it's very crucial to be aware that the manipulator does not cross through any singular positions, right? Because that would basically destabilize the control system. So after kinematics, we moved on to dynamics, in which we have involvement of the inertial or the dynamical properties. So in the last discussion hour, we saw that how inertia matrix is described as a 3 cross 3 matrix, and what are the principal values and the principal moment of inertia, and what's the principal axes, and how they relate to the eigenvalue and the eigenvectors of the inertia matrix. And then we started finding relations between the accelerations, velocities, and positions, and the external forces and moments. So basically, we are relating the agency of force, that is the forces and moments, to the outcome of that agency, that is acceleration. So and this relation is called as the equation of motion. So if for a system we know the equation of motion, so then we say that we know the dynamics of the system, because if I know the forces, then I can calculate the accelerations, and hence I can and given us known starting configuration of the manipulator or of the system, we can integrate to find velocities, and then from velocities subsequently we can find positions. So so the entire dynamics of this rigid body multi-body system is condensed in form of the equation of motion. So the entire kinematics and dynamics, the entire, I will together call them as kinodynamics. So the entire kinodynamics is summarized into these two things. First, you have the you have found out the uh, Jacobian for any point of interest, and secondly, you have the equation of motion, which basically describes the relation in form of something like this: x dot is equal to f of xu, where x is the state and u is the external control input. So this is more of a control nomenclature. So u is the force or the torque, and x is your q dot and all those things. So once we have this, we say that we have the mathematical model of the system. So this is at this stage. Let's say you start analyzing, a completely new system. So when will you say that you have the mathematical model of the system? So this is the point where you say that you have the mathematical model of the system, and now you are at a stage where you can basically start actually planning. Basically you can start going towards application, and for application you would need the robot to move reliably from one point to another following a certain trajectory. And at this point, the concepts of motion planning and control come into the picture, right? So after this point, right, once you have the model, you have made the so you started with the physical system, then you simplified it in terms of, let's say, some linkages connected via joints. Then you made assumptions that the joints are ideal, that is they are frictionless, and the links are rigid, they do not deform. And then following the steps that I just outlined, you have finally arrived where you know the Jacobian of any point on that system as a function of the joint angle, and you have the equation of motion. The general form of the equation of motion, I'll just write here that mq double dot plus cq dot plus g is equal to tau, where uh, where the terms on the left hand side, the first term on the left hand side is the inertial term. M is the joint space inertia matrix. It's a positive definite symmetric matrix. Then the second term is CQ dot, which basically includes the nonlinear effects, that is the centrifugal and Coriolis effects. And G is the gravity term, basically, which describes what is the contribution in joint torques due to the manipulator's own weight felt due to gravity, right? And on the right hand side, we have the joint torque vector. And here also we have the concepts of forward dynamics and inverse dynamics. So so forward dynamics is when we know the agency, that is the forces and the moments, and we calculate the accelerations, right? And inverse dynamics is when we know the accelerations and we calculate what force or moment has caused this acceleration. So that is the forward dynamics and inverse dynamics. And for finding the equation of motion, we saw the Lagrangian approach. It's an energy based approach, the Lagrangian approach, energy based, right? So we saw that Lagrangian is described as the difference of the kinetic energy and the potential energy of the system, and by using the Euler-Lagrange equation, we can find out the relation uh, between the accelerations of the degrees of freedom and the forces along or about those degrees of freedom. So at this point, what all things you can do is that if I give you the position, let's say if I give you that you have a 2 hour manipulator and the ang so let me just describe this example that at this point what all things you can what you can do by employing the concepts and uh, ideas that we have discussed. So let's say you have a 2 hour manipulator, the simplest of systems, where these are the angles theta 1 and theta 2. This is the end effector, right? So let's say if I give you the position of the end effector pxy and the lengths L1 and L2 and everything else is known, masses, inertia, assume everything else is known about the system. So if I give you the position of the end effector pxy, then you can quickly tell me what will be the angles theta 1 and theta 2 by using inverse kinematics. And if I give you theta 1 and theta 2, you can tell me what will be the position of the end effector pxy by using forward kinematics. And then if I give you again the velocities of the end effector, then you can use Jacobian to find out the joint velocities, and again vice versa. And then since I have also given masses and inertia of each of these links, you can you can calculate the equation of motion and basically come out with equations that tau 1 is a function of this, tau 2 is a function like this. So relating the accelerations of the joint, the velocities of the joints to the joint torques. And if I say that this much torque has to be generated, or this much torque has to be is being applied on the end effector, then you can tell me that what and in a certain configuration, then you can tell me that what would be the accelerations of each of the joints. And if I say that the force is being applied for certain time, then you can basically integrate those accelerations to find out the velocities and again the positions. So uh, basically at any instant you can analyze the kinematics and dynamics of the system, of any system. This is the simplest 2 hour manipulator system. Now now we will be concerned that first, how do we want to move our end effector in order to achieve a certain task? Because now in each of the analysis that we have seen, we have taken a snapshot of the manipulator, that it's an instant basically. So that let's say an instant where theta 1 is 30, theta 2 is 60, it's an instant, right? There is we are not analyzing continuous motion as such till now. We have just analyzed configurations or certain the instantaneous configuration of the manipulator. Now from this point on, we will be interested in the continuous motion of the manipulators. So first we will see, so so what we see now is continuous motion of the system, and that brings into the picture the concept of motion planning, and brings into the the very broad and deep field of control design. So motion planning and control design of manipulators is something which we'll be covering in this and the upcoming discussion hours. So at this point if you have any questions, then please let me know about any of the the entire overview that I described. If any part of it you want more clarity on, then you can let me know. Otherwise we will start our discussion of motion planning. Okay, perfectly fine. So as I said that now we will discuss about motion planning, and the first thing which basically comes up commonly in discussions is that what is motion planning and what is path planning, right? So this is a question which I have discussed with students many a times, and uh, sometimes people are still you know are not aware about the distinction, and they are loosely used interchangeably. So first let's uh, be very clear and describe that when say path planning, then what is meant, and when I say motion planning, then what do I mean. So basically path planning has no time information. So suppose this is a map, and you are at point A and you have to go to point B, and there are some regions which have obstacles, right? Obstacles, and let's say you choose this as the this so avoiding all the collisions, this is something which you can follow to reach from point A to point B. Now just this set of points, as you can say, points or poses. So let's say this is a mobile robot or the end effector of the manipulator. Let's say if a manipulator is working on picking objects in this workspace, so the end effector's frame can be oriented like this and placed at these points, then it will avoid collision. So that's the path, right? So path would be just what sequence of end effector poses that should be followed in order to reach from point A to point B while avoiding these obstacles. On the other hand, when I say motion planning, so that brings into the picture the factor of time. And times when time comes, we have velocity and acceleration into the picture. So now I am describing uh, the position of the end effector, the velocity of the end effector, the acceleration of the end effector. So I'm not only saying that it has to move from this pose to this pose to this pose and finally here. I am also saying that it has to move this fast from here to here, then maybe change its velocity between these two frames, and then so forth and so on. So I am providing information about the uh, how fast also we are moving, and basically at what time instant we reach these different poses. And when we have time based information, we call them as trajectory. So here we in path planning we find out a path, a sequence of poses, and in motion planning we are concerned about trajectories, and trajectories are always written as a function of time, right? So that's what is mentioned here also, that time history of position, velocity and acceleration of actuated joints or the end effector, right? So let me just write that down here as well, because that will form our basis of the discussion. So time history of the position, velocity, acceleration of the end effector or the actuated joints. So that is known as the trajectory. Now here the key terms that are there, uh, that we would like to highlight is, first is time history, and then position, velocity, acceleration, and then we have the end effector or the actuated joints. So time history we saw here just now. I described that we are describing that, okay, at point t is equal to 1, the position is this much, t is equal to 1.1, the position is this much, t is equal to 1.2, the position is this much, and so on, right? Similarly, a history of time history of velocities and accelerations, that is trajectory. And uh, now this position, velocity, and acceleration, right, can be specified for the end effector or for the actuated joints. So if we have a manipulator like this, so this is L1, L2, and we have theta 1 and theta 2, then, and this is the end effector P, XY, then I can either specify in the EE space. So I can either specify what is x as a function of time, y as a function of time, and then x dot as a function of time, y dot as a function of time, and then x double dot as a function of time, y double dot as a function of time. Or I can specify in the joint space, the two spaces that we have seen before as well. Or we can specify that what is theta 1 t, theta 1 dot t, theta 1 double dot t, and what is theta 2 t, theta 2 t dot, and theta 2 t double dot. So so what we are trying to achieve here is that we are trying to describe the position, velocity, and acceleration of the end effector, or we are trying to specify the joint angles, joint velocities, and joint accelerations for each of the joint of the robot, right? So these are the two ways in which we can specify the trajectory. One is the E space, which also known as the Cartesian space or operational space, and this is the joint space, and yeah, usually known by this name itself. So you can see that if I want to, and generally we want a certain type of motion from the end effector. Okay, so we can keep on switching between these two spaces, between the E space planning and the joint space planning, depending on our ease and convenience, and which is more intuitive for us to use. We can keep switching between them. So uh, so yeah, this is joint space schemes. These are time history of single or multiple joints, and then we have the Cartesian space or the end effector space schemes, in which we have time history of position and orientation of the end effector, right? So now, while specifying trajectories, what all informations we generally have a priori before we actually find out the trajectory. So generally we have the initial and final points, again in either joint space or Cartesian space. So in joint space it would be the initial angle and the final angle of the joints. In Cartesian space it would be the initial and final position of the end effector or the orientation of the end effector. We can also specify the initial and final desired velocity, uh, and we can also specify that these are the few points through which the end effector or the joints must pass through, right? So that is and an extra layer of information. And what we also want is that trajectory should be uh, you know continuous at in terms of acceleration. So that is known as the C2 continuity. So which means that the function that we are using to describe the trajectory of the joints or the end effectors, the second derivative of that function should be continuous across the between the final and the initial points. So that is so it, basically if the acceleration is not continuous, then there would be sharp changes in the velocity, and the profile is the profile or the motion of the end effector becomes very jerky. So let's get back to the discussion here. So uh, yeah, we saw that we we usually know. So usual info that we have is initial and final position. Final, like, when I say position, it can be, so I mean it can be either end effector position if it's E space, and it can be joint position if it's joint space. Then we have the desired velocity, initial and final. So basically, let's see first. Let's see the joint space schemes because they are easier to understand mathematically. They are much more simpler. So let's say we have a 2R manipulator. So we have theta 1 and theta 2. Okay, so let's say we have the initial position as theta 1 0 and theta 2 0, and the final position as QF. So that is theta 1 F and theta 2 F. Right, so now let's analyze one joint. Let's analyze one joint at a time. This, and since these joints can be controlled independently, we can do the same calculation for other joints as well, if they are revolute joints as well. So basically the first joint that we have, it the initial value is theta 1 0, and the final value is theta 1 F. Now, a very simple approach could be that we can do linear interpolation. That this is theta 1 0, this is theta 1 F, right? So this is the starting point, this is the ending point, and what we also have is the very important information, the time duration. We have to, so we must know that if we have to move from point A to point B, then we want to move it in what time, because that governs the velocities and accelerations, right? So if we have, uh, let's say we have time t0 here and time tf here, right? So, and then at any time t, what is the position of that joint if we are using linear interpolation? Linear interpolation, the very basic one. So the delta that we have to cover is theta 1 f. I will drop this one notation and I will just write theta f and theta 0, because the same can be done for any joint. So this is delta, and delta t is tf minus t0. So this is our independent variable time, and this is our dependent variable theta, because we have the function like this, theta as a function of t, right? So theta t can be written as, and you can verify this expression, we have theta 0 plus, we have to cover theta f minus theta 0 in tf minus t0, right? And the time can be t, the current time minus t0, right? So this is the expression for theta t if we are doing linear interpolation. So you can see that, you can check the boundary conditions, that the theta t0, this t0 minus t0 will become 0. So theta t0 is in fact theta 0 as we want to keep, and theta tf, we have tf minus t0, so this cancels out, so it is theta 0 plus theta f minus theta 0, so it is theta f. So this checks out, this checks out, right? So now in the case of a line, so basically this is a, in joint space, this is a straight line between theta 1 and theta 0 and theta f, right? And we know that we know that a straight line can be represented uniquely like this: y is equal to mx plus c. Right? Or so this is the slope and this is the intercept. Now this means that let's say if I have these two unknowns, m and c is unknown about this line that joins theta 0 and theta f, right? So we have two unknowns, and if we to find out these two unknowns, we must have two equations, right? So two unknowns can be found out, by taking two equations. So the two equations are basically that at t is equal to 0, so let us find out that equation in another way. This equation that I just found out. So we know that at t is equal to 0, it should be theta 0, and at t is equal to f, it should be theta f, right? So what we will write is theta 0 is equal to m t0 plus c, and theta f is m tf plus c, right? So we have two equations and we have two unknowns. We have unknowns m and c. All right, so what we can do is we can subtract, we can do a minus, or we can do b minus a, so it will be theta f minus theta 0 is equal to m tf minus t0. Very straightforward. So m is theta f minus theta 0 by tf minus t0. So that's how we get m, and similarly we can get c as theta 0, right? So the idea of what I want to illustrate is that for a linear path between 2 points, we can only have two boundary conditions. So we can only have two boundary conditions. Either we specify theta t0 and theta tf, the position at the initial and the final time, or what else we can specify. Only two things can be specified. What else can be specified is that either we specify theta to 0 and what is the velocity, the constant velocity that we want to achieve. Because if you see that a linear path has a constant slope, so it is a constant velocity profile. So if I draw, this is a plot of t, this is theta, this is theta 0, this is theta f. So this is the so this is tf, this is t0. So if this is the profile of theta t, then the profile of theta dot t is so a constant velocity, basically like this, and then it becomes 0, and then it 0 basically. So 0 0, this is v0, this is t0, this is tf. So you see here is that there is a sudden jump step in the velocity, that the velocity is 0, and as soon as the motion will start, the velocity will go to a certain level, then be there, and then at the end of the motion suddenly comes to a rest, right? So linear profiles are generally, not, they are very simple. So for if we are going very gradually, they would work fine, but generally they are avoided because they will, at the start and the end point, they will lead to a jerky motion, because the velocity is, and if the velocity is like high enough, the end effector or the manipulator would suddenly get a steep velocity, then move with that velocity, and then come to a rest abruptly. So that is the uh, linear profile. Now similarly, what you can do is that, so basically what the idea you can get is that we can choose any polynomial. We can choose, so polynomials are a good choice because they are differentiable. They are differentiable n number of times. So any polynomial of any degree, right? Any polynomial, any degree, and higher the degree, more the customizability. So more conditions can be applied or enforced. You have freedom to enforce more conditions on the trajectory. So you can have quadratic. So quadratic, it will be theta t is equal to at square plus bt plus c. So here the parameters are a, b, c. So three parameters, so you can specify three conditions, right? And then you have the cubic ones, which is at cube plus bt square plus ct plus t, right? So a, b, c, t, 4, right? So 4 conditions. And this is one of the very common choices, because in the four conditions what we can do is two position and two velocity at each endpoint. So basically what we can do is we can specify the position at the start point, position at the end point, and then velocity at the start point and the velocity at the end point. So let's go into depth of the cubic profile. Right, so theta t is a different notation is being used here. A0 plus a1t plus a2t square plus a3t cube. T belongs to t0 to tf. And we have these four conditions that we have known position. So the starting position is known, the ending position is known, the starting velocity is known, and the ending velocity is known. So we have four unknowns, and we can get four equations, as you will see right now. So what we discuss now is so cubic trajectory. I'm writing once again. Let me use the same notation: a0 plus a1t plus a2t square plus a3t cube. T belongs to t0 to tf. So the boundary conditions are theta t0 is theta 0, theta tf is theta f, theta dot t0 is theta 0 dot, and theta dot tf is theta dot f. Now usually many a times the theta dot 0 and theta dot f is kept as zeros, because many times you want motions in which the joint starts from the rest and then at the end of the motion then again goes back to rest. That is zero velocity. But we can derive the results for a general case. So basically we would write these conditions. So first let's also write what is theta dot t. So theta dot t is a1 plus 2 a2t plus 3 a3 t square. Now we can use these four conditions. So first is a0 plus a1 t0 plus a2 t0 square plus a3 t0 cube is equal to theta 0. Then we have a0 plus a1 tf plus a2 tf square plus a3 tf cube is equal to theta f. Then we have the two velocity conditions, that a1 plus a2 t0 plus a3 2a3 t0 is theta dot 0, and a1 plus a2 tf plus 2a3 tf is equal to theta dot f. Now these are basically four linear equations So the unknowns are these a0, a1, a2, a3, right? These are the unknowns, the parameters of the cubic curve. So four linear equations and four unknowns. So linear equations, this is a system of linear equation. So this can very well be described as a in a matrix vector product. So our parameters are a0, a1, a2, a3. This is theta 0, theta f, theta dot 0, theta dot f. So we can write the coefficients here. So it will be 1 t0, t0 square, t0 cube. Then for the second it would be 1 tf square, tf, no, tf. So tf square and tf cube. Then it would be 0 because the first coefficient is gone. Then 1, then t0 and tf here, and then here 2 t0 and here 2 tf. Okay. Oh, I made a mistake. Here it would be 2, 2, and here it would be 3, 3, and here square, and here square. So let me correct this. So here would be 2t0, here 2tf, here 3 20 square, here 3 tf square. Right. So this is tf 1 t0 tf t0 t0 square t0 cube 1 tf square tf cube 1. Okay. So this is basically the system of equations. This is A, this is our parameter set X, and this is our residual B. So we can find out X by doing X is equal to A inverse B. So this is how you can do in like numerically if you want to do it. We can also find out very easily with like some manipulations. We can solve out and write down the analytical equations of these four parameters, so which show up like this. So a0 is theta 10, and this is basically for t0 is equal to 0, because then the equations basically get very much simplified, and this is a very valid assumption. We can keep t0 is equal to 0. So for t is equal to 0, t0 is equal to 0, we have a0 is theta 10, a1 is theta dot 10, and this is a2 and a3. So this is how. So basically, if I want to move the manipulator from, let's say, theta is equal to 30 degree from to theta is equal to 60 degree, and let's say in 2 seconds Then I can use this equation to find out my uh, cubic profile of that joint, and then I can basically sample that trajectory at certain frequency, let's say 200 hertz. So like at every 1 by 200th of a second, I put the value of t in the equation of theta t and get the value of theta, and I command that theta to my motors, right? And that's how the motors move in that profile. So that's how we make use of these trajectories. So we can do very basic simulations using these trajectories. So this is where I will conclude for this discussion R. Right, I encourage you to take some boundary conditions on your own and try to find out trajectories and plot them in order to visualize how the trajectories look. And you can play around with the boundary conditions. You can try by keeping the boundary conditions, both the velocity boundary conditions as zero. So you'll see that the slope at the start and the end does in fact is zero. So that's how we will plan in the joint space. A similar thing we can plan in the Cartesian space, but in Cartesian space we will get a trajectory of x as a function of t, and then we'll have to use inverse kinematics to basically find out what is theta as a function of t, and then we will command those theta angles to our motors. So this we will use as a foundation for developing control algorithms, which we will discuss in the next discussion hour. Thank you for watching and have a great week ahead.